Welcome back to Civil Engineering Academy. This is Matt, and today we work a problem from the Water Resources Depth section of the Civil PE exam. So let's get going. The following table includes data recorded at a stream monitoring station after a 3-hour storm which produced 1.5 inches of runoff over a 120-acre drainage area. Find the peak stream discharge following this storm. So if we look at this problem, we realize that it has to deal with hydrology. And section 6.5 of the PE reference handbook, and at the time of this recording, we're using version 1.1 of the reference handbook. 6.5 of the handbook is the hydrology section. But if we look in this section, we don't see any equations that explicitly help us solve this problem. So what we need to do is we need to use our engineering judgment and our knowledge about water resources and hydrology to arrive at the right answer. So whenever we're given a table like this, we have discharge and time, we need to look at the discharge value at time 0. And if this value in this position is any other number besides 0, we know that the stream has a base flow. And a base flow refers to water or flow that's always flowing in the stream regardless of any precipitation or storm activity. So in this case, we see that in the time 0 hour, the discharge is 18. So that means that this stream has a base flow of 18. So the first step, what we need to do is subtract the base flow from each discharge value. So what we'll do is we'll subtract 18 from the discharge value at time hour 0, hour 1, hour 2, all the way through. So we'll just make another row and we'll calculate the discharge without base flow at each of these time hour intervals. So at hour 0, the flow would be 0. The discharge would be 0. At hour 1, the discharge would be 24 because, again, we're subtracting 18 from each of these. So at hour 2, the discharge is 43. At hour 3, the discharge is 106. At hour 4, the discharge is 90. At hour 5, the discharge is 64. And at hour 6, the discharge is 19. So now what we're going to do is we're going to calculate the total volume of runoff. So what we'll do, calculate the total volume of runoff from the storm event. So what we've done in step 1 is we've gotten the discharge at each hour interval just from the storm by subtracting out the base flow. So what we'll do in step 2 is we'll calculate the total volume of runoff, and that is equal to the sum of all the discharges, hours 0 through 6, times delta t, which is the time step interval, which in this case is 1 hour, because between time 0 hours and 1, that's 1 hour, 1 and 2, that's an hour. It's increasing by an hour, 1 hour at each interval. So we'll plug in and we'll solve for the volume of runoff equals the sum of all the discharges. So if we sum up 24, 43, 106, 90, 64, and 19, that's cubic feet per second. All these values have the units of cubic feet per second. That is 346 cubic feet per second times the time step interval. Well, we know that the time step interval is 1 hour, but we need to do our unit conversions because we're given the runoff in cubic feet per second. So we will take 60 seconds per minute, multiply that by 60 minutes per hour. So our seconds cancel, our minutes cancel, and then the time step is just 1 hour, right, from the problem. We just talked about that. And so that gets a total volume of runoff equal to 1,245,600 cubic feet of total runoff. So that's a lot of runoff. Then what we're going to do is we're going to calculate in step 3, we're going to calculate our average runoff depth. So average runoff depth. And again, we don't see any specific equation to calculate this specifically, but we know that the depth, we can calculate that by taking the total volume, which we just found in step 2 was 1,245,600 cubic feet. And what we can do is divide that by our area. And so, what's the area? Well, if we look up at the problem statement, we see that we're given the area of a 120 acre drainage area. So if we take 120 acres, and in section 1.2 of the PE reference handbook, we have our unit conversion factors, and we know that 1 acre is equal to 43,560 square feet. Again, that's from section 1.2 of the reference handbook. And what we'll do is we'll then take our 1,245,600 cubic feet and divide it by close brackets, because we're going to do our unit conversion first, 120 acres times 43,560 square feet. And that gets us an average runoff depth equal to 0.23829 feet. And we want it in inches because runoff is typically measured in inches, so we will just multiply that by 12 inches per foot, and that gets us an average runoff depth of 2.8595 inches. So then from there, what we'll do in step 4, we're going to calculate the peak runoff discharge. So write that down to keep us on track of where we're going. So the peak runoff discharge. And if we look at our runoff values, we need to find in which hour the peak discharge occurs. So if we look at the values that we've arrived at after we subtract the Baseflow, we have in hour 0 is 0, hour 1 discharge is 24 cubic feet per second, hour 2 43 cubic feet per second, hour 3 106 cubic feet per second, hour 4 90 cubic feet per second, hour 5 64 cubic feet per second, and in hour 6 19 cubic feet per second. So we can see that the peak discharge occurs in hour 3, where we have a 106 cubic feet per second discharge. So we're going to take that value and we're going to plug it in down here in step 4, and we're going to take 106 cubic feet per second, and we are going to multiply that by 1.5 inches. And we get the 1.5 inches from the problem statement because we're told that the storm produced 1.5 inches of runoff. So that's very important because that plays into this step 4. So we're taking our 106 cubic feet per second times 1.5 inches, and we're going to divide that by the average runoff depth that we found in step 3 of 2.8595 inches. And at this point, we will arrive at an answer for step 4 of 55.604 cubic feet per second. But we have to be careful because we're not finished yet. First off, let's check back here in step 4 and let's make sure our units work out. So we had the 106 cubic feet per second discharge times the 1.5 inches in the numerator. Then we divided that entire quantity by 2.8595 inches. Well, our inches cancel out, and that leaves us with 55.604 cubic feet per second. So our units work out in that. But we know that in step 1 up here, we determined there was a base flow of 18. Remember that? So we're asked in the problem to find the peak stream discharge following the storm. So we said base flow is always occurring. So that means in step 5, to solve this problem, ultimately what we need to do is we need to take our peak runoff discharge that we found in step 4. Remember, the runoff discharge is from the storm itself. And we need to add back into the 55.604 cubic feet per second the 18 cubic feet per second of base flow. So plus 18.0 cubic feet per second, that's our base flow. That base flow is always occurring in the stream regardless of if there's a storm or not. So if we're talking about discharge during or after a storm, it's going to include the storm discharge plus that base flow, and that gets us a final answer of 73.6041 cubic feet per second. That will be the peak stream discharge following the storm. And if we look back up at the answer choices, that is closest to answer choice C. And we've successfully solved this problem. So a very in-depth problem dealing with base flow and from our water resources depth section. So if you're looking for more practice and review in your civil PE exam preparation, head on over to civilengineeringacademy.com and check out our ultimate breadth and depth civil PE review courses, and we'll see you there.